Okay, so last day we looked at something called electric forces. Now we're going to look at something called an electric field. So for us to understand electric field, let's start by going back and thinking about what is a gravitational field. Electric field, same idea, I'd say. So a gravitational field, imagine we're on the surface of the Earth. So this is the surface of the Earth. Surface of Earth. We know that if we were to drop something on Earth, it just falls to the ground. So the gravitational field, we know that there's something that is causing objects with mass to move towards that surface. If we zoom out and look at the Earth, like so, here's our Earth. And if we drew lines towards it, like we know if we put something in space, like over here is this dot, it's going to move towards the Earth. It's going to fall towards the Earth. So I can draw what we call gravitational field lines that point towards the Earth. And you can just keep drawing in those lines. Like so. So the interesting thing about field lines, for one, they serve two purposes. The first purpose is to show the direction of the field. So how gravitational field lines work, they tell us the direction that if I were to place a second object, something with mass, so for example, we put something right here all of a sudden, it tells the direction that it will move. So the gravitational field lines tell us the direction that an object with mass will move when placed within that field. The second purpose of gravitational field lines, they qualitatively show the strength of the field. So basically, the closer together the lines are, so notice how if we look at the spacing between the fields when they're really close to the Earth, they're actually quite close. You see how close they are. But if we zoom out at the further away, we can see that the distance between the lines further away is greater. So they qualitatively show the strength of the field. So the closer the lines are, the stronger the field. The further away, the weaker the field. So on the surface of Earth, we get these parallel lines because we know that it doesn't matter where we are near the surface of the Earth, that value is 9.8. Like we know the gravitational field strength, 9.8 meters per second squared. Doesn't matter where we are. Anywhere on Earth, that is our field strength. But if we look at the zoomed out version, like right near the Earth is 9.8, but as we get further away, so maybe out here, it's actually only a value of like 6.7. So another thing that has field lines are magnetic fields. So for example, if we have a bar magnet, north and south. The Earth itself is actually a giant bar magnet. The North Pole is the magnetic south. The South Pole is the magnetic north. So here's our North Pole up here. Here's our South Pole down here. So we've all kind of experienced this before. We've hopefully all used a compass before. What a compass does, it aligns itself in the direction of the magnetic field lines. So what happens is magnetic field lines travel from the north to the South Pole. They go from the north to the south. North to south. So again, our what we call the North Pole is actually the magnetic South Pole. So they actually have a little bit reversed in that. If we look at this bar magnet, field lines go from north to south, north to south, north to south, north to south. So we can just keep drawing in those lines. Drawing in those lines. Okay, they're going out. If we had two bar magnets that are coming close together, so a north and a north, we know those are going to repel each other. What do our magnetic field lines look like? They look something like the following. They get repelled. It does not want to come towards each other. So they repel one another. So that is what our field lines look like. For electrostatics, we're looking at charges. So we scroll down. So let's look at some examples. So let's say we have a positive charge and a negative charge. So let's look at a couple different examples. So we have this one right here. We know it's the field line points itself in the direction of positive to negative, positive to negative, positive to negative. So when we look at gravitational field lines, they tell us the direction that something with mass will move. So you know that if we put something on with mass near a planet, like Earth or Mars or near the moon, for example, we know that that object is going to travel towards the Earth or moon or whatever it's close to. So for this one, what field lines tell us, it tells us the direction that a positive charge would move. So for example, if I were to place a charge right here, let's say if I put a positive charge, this blue thing right here, let's say that's blue and it's positive. If I were to place it right there and it's starting stationary, what's going to happen is that that positive charge would cause it to repel. But at the same time, that negative charge way out there, it's going to cause it to attract. So it's going to end up that blue charge will follow that path. It's going to show us the path it's going to travel. Same thing as what we saw last day. If we put a charge right in between, that's positive charge. That positive charge is going to push it away, but at the same time, the negative charge is going to attract it. So we know it's going to move towards the negative charge, that positive thing. So these field lines tell us the direction a positive charge will travel. So I know it's the direction of a positive charge. If I were to put a negative charge, so for example, let's say I had a negative charge. Let's use a green. Say I put a negative charge out here. If this was a negative charge, it's going to, the electric field lines tell me are pointing one way, but negatives just travel in the opposite direction. So a negative charge will travel in the opposite direction of our field. Let's look at a few more examples. Let's say if I just have a negative charge like so, negative charge is actually just like behaves just like a planet. We know that it's going to attract positive stuff. A negative charge attracts positive stuff. And what happens if we have some weird combination? So it could be whatever combination. Say we have a negative, positive, and positive. So what's going to happen? We know that if we have a positive and negative, just like the first one we drew, that is going to draw a line that goes from positive to negative. So I know there's going to be some field line that goes towards there. So like it's going to attract it like so. But we also have two like charges, they're going to repel. So a field line will probably likely come out of this positive charge, but it's going to be repelled from the other positive charge and go towards the other negative charge. Negative charge. So these positive charges are going to repel, and it's going to attract. So positive to negative, so you're going to have that attractive. One thing to note is if you look at all my examples, my electric field lines or all my field lines, they never cross. They never cross. So what I mean by that is a charge will not, let's say a charge was starting right here, it will not spontaneously go up or down like that. It's not going to happen. So that would not happen. It's just going to follow that path depicted by that electric field line. So let's do a few more examples just because. Let's say we have a negative, positive, negative, positive, like so. You know, positive goes towards negative, positive goes towards negative, positive goes towards negative. And we'll just end up with these different scenarios. Okay, so they're never going to cross. I'll try to squeeze that in. Again, never going to cross. So if I do accidentally cross any two lines right now, that's purely accidental. Okay. Another thing that we'll look at later in this topic is something called a capacitor. Capacitor is a charged plate. Let's say I'm able to positively charge one end and negatively charge the other end. So we get what's called a capacitor. So some of you that may have studied robotics or done a little bit of circuits, In the tech classes, you might be a little familiar with this. What it does, it creates what's called a uniform electric field. So in between, we get a constant value of electric field. However, it does begin to break down as you get to the edges, starts to behave like a point charge at the far edges of the capacitor.